Hey everyone, it's Larry here, and I hope you're all having a wonderful day. This is my first video in a series where I'll walk through notable submissions from the Reserve Hackathon that concluded in January. I'm going to ease into this with a submission I'm very familiar with, because, well, it's mine, the Reserve Zap. This video is going to be structured in two parts. The first illustrates how the zaps look on the UI, and the second is a technical deep dive on how the contract code works. So let's dive in. So what we're looking at here is the GitHub pull request for the Reserve Zap submission. It includes a nifty little graphic that I think explains the motivations of this project pretty well. On the left, the guy is grumpy because he's got to obtain each of the individual collateral assets in the right proportion in order to get the RToken. So this could be 3 different tokens in this case. On the right, the guy is happy and chilling because he can zap in with any single one of his desired tokens and get an RToken that way. So let's check out how the site works. What we're looking at here is the Register app extended with Zap functionality. And for this example, we're going to try to mint the frictionless token. Let's say we want to zap in with USDC. And in the normal case, without zaps, the user would have to get the right proportion of C DAI and deposit both of those to get his RToken. But now we can do so with only USDC. So we confirm this transaction, and we will see that the balance has increased to 325, and that's great. And the benefits of the Zap work in reverse as well. If by default, if the user were to try to redeem, they would get the whatever proportion of C DAI and DAI. But say they didn't want that. Say they wanted USDT. The Zap will enable the user to get whatever token they'd want out without having to convert it after the fact. So let's confirm a couple transactions. And voila, you'll see that the user's USDT balance has increased. And so that concludes the UI walkthrough component of our presentation. And we're going to move on to the fun part where we explain how the contract code, which powers the zaps, work. And I thought the best way to do this would be to show a diagram of the token flow of through all the different components in the system. In this example, the user wants to enter an RToken comprising equal parts ADAI, CUSDC, and ETH. And he could do so with any one of these tokens, but in this example, he will use Frax. So the user will deposit Frax into the Zapper contract. The Zapper contract forwards the Frax to the Zap router, which contains all the swapping logic. It will individually swap with Curve for each of the constituent tokens, which are USDC, DAI, and ETH. And at this point, we're good for ETH because the RToken uses naked ETH, but not quite so for USDC and DAI. It needs to be wrapped into their proper lending market tokens first. And so we have what are called router adapters shown here, and specifically logic for Aave and Compound. The Zap router will deposit into each respective protocol and get the proper wrapped token. And the logic is defined specifically for each relevant protocol. And so now the Zap router has all the tokens we need to obtain the RToken. It will forward these back to the Zapper, and the Zapper is aware of Reserve's states, as in the proportion of tokens that are required and in what form. And so once it's satisfied, it forwards all of these to Reserve, mints an RToken, which is passed on to the user, thus concluding this flow. And so now let's jump into the contract code itself. What we see on the right here is zapper.sol, which corresponds to the first step of this guy here. I've collapsed all of the main functions so that we can go over them at a high level first. We have zap in, zap out, zap to collateral tokens, and get lowest issue ratio. These two, zap in and zap out, are pretty self-explanatory. They are the user's point of entry into this contract and are the external functions. Zap to collateral tokens routes each trade from the Zapin asset to each of the collateral assets. And get lowest issue ratio determines what the possible amount of RTokens that can be minted is. So let's have a peek into Zap in. The first step is to transfer the tokens from the user, no surprise. The next is to zap to collateral tokens, which is this internal function here. It first queries the basket's basket breakdown, which tells you what the ERC20 collateral assets are and their proportion within the basket. It does a bunch of math, loops through each of these, and the important part to note here is the zaprouter.swap call, which individually zaps for each of the different collateral assets. And so once it's obtained that, we're back in Zapin with the tokens we got and the amount that we got. It then calls lowest issue ratio to know what the actual balance we're trying to mint is. And the way get lowest issue ratio works is it relies mainly on the basket handler contract of the RToken. It does some pretty funky math to determine, and this is lifted from the basket handler code itself, but it replicates it to find out what can I reasonably obtain based on the number of collateral assets I have. And it will call this quote function to figure out those theoretical quantities, and you're going to look for the lowest ratio, because anything higher than that, and you're not going to have enough of some other token. And then we're back in Zapin. Finally, it will call RToken.issue, which sends all of those collateral tokens to the RToken contract and gets in return an RToken. And after that RToken is transferred to the user, and unused amounts of the Zapin token are refunded, and also the collateral assets that were not used. So if we go back to the high-level flow diagram, you'll see that all the functions in Zapper have been explained. The Frax token is sent to the Zap router, and all of the different collateral assets are returned. The Zapper then sends these collateral assets to Reserve, and the RToken is minted and sent to the user. Now let's have a look into how the Zap router executes these swaps. And like before, I've collapsed the main functions, which are swap and build swap params. Build swap params is a helper function which abstracts some of the complexity of dealing with Curve and in constructing the payload. What that means is you basically have to send, based on the token routing of the trade you want to do, say from Frax to ETH, you have to send the relevant pool addresses and the indices within each respective pool. So for example, if you were to trade Frax into ETH, it would first route through the Frax base pool comprising Frax USDC, and then it would route from USDC to ETH. And this, basically, it's kind of ugly, but it finds out those different variables for you. And the main thing I think that's more interesting in this contract is a swap function. This is the entry point that is called by zapper.sol. And if we recall the overall flow, we're now looking atomically at a single token and swapping it for another single collateral asset. So for example, we're doing a swap from Frax to the particular amount of ETH. And for the 3 tokens in that pool, this is going to be repeated 3 times. So first, it transfers the Zapin token from the Zapper. And we see here that we're now dealing with these get router adapters. What this does is we want to see if the input token and the output token needs to behave in a particular manner that's not accommodated by Curve. So for example, it could be Aave or Compound, where the token needs to be wrapped or unwrapped from its lending token equivalent. And if so, for example, if the from adapter address is not 0, meaning we've registered an adapter on that particular token, we have to unwrap in order for it to be able to be consumed by Curve. And so the next interesting portion is this Curve exchange provider get best rate method. I'll explain a little of what the exchange provider is first. It's instantiated here and is essentially a dictionary of all the different pools and tokens associated with Curve. And it's a centralized place for us to obtain relevant pools and routes that we need to interface with Curve. This get best rate is asking Curve, hey Curve, I want to send you Frax and I want to get ETH in return. Can you do that for me? If it can, it will give you an exchange pool, which is an address, and an exchange amount, which is the amount of tokens you're expected to receive. However, this is only the case, it works in only the case where there's that direct route. If exchange pool is not available, it returns address 0, and so we have to do a little more work to enable multi-hop swaps. But let's talk about the happy path for now. It gave us a suitable exchange pool, and it goes into this else block where we can simply perform that swap, and we're happy. If necessary, we can unwrap it using the adapter to whatever output token it needs to be. Sorry, I meant wrap. And in the case that multi-hop swaps are required, we can build these out in 2 steps. We can find the intermediate token using this exchange pool hop 1 and then subsequently with pool hop 2. So we do this by hard coding USDT to be the intermediate token. And so the reason USDT is chosen is because it's the stablecoin that's part of the TriCrypto pool, which sort of serves as the entryway to all of the different crypto assets. That is to say, the non-stablecoin assets. So for example, if you wanted to get Frax into ETH, you would have to convert Frax into USDT first, and then go through the TriCrypto pool to finally end up with ETH. And that's all handled here, and you will finally still get what you need. It just takes a couple more steps. And voila, you have received a single collateral asset from this swap. And this is repeated all the times for the different RTokens in the basket. Sorry, for the different collateral assets in the basket. We're really close to being finished now, and there's just one last piece we have to deal with, which are those router adapters we mentioned. So let's check one, for example, router adapter. Look at Compound. So first of all, router adapters are registered on the Zap router so that it knows, when it's dealing with a particular token. We also need this additional step of doing some router adapter logic. And this Compound one, in this particular example, the Curve will give us back USDC and DAI. But for the RToken, we need Compound DAI. How do we get that? We wrap it using this function. And there are Compound-specific methods that we interface with in order to do so. So if we go back to Zap router, we look at the wrap function. The 2 is USDC, for example, and that's the amount. And in this contract, we're going to wrap that USDC into CUSDC, or sorry, in this case, it's CDAI. And that is done with a compound specific method of mint. And this is the logical equivalent of a user depositing their DAI tokens in Compound and receiving that CDAI in return. Finally, that token is transferred back to the Zap router and ultimately back to the Zapper so that it can send all these tokens to the RToken in the issue call and get the RTokens we need. And that concludes our walkthrough of the code. If you've gone this far, thanks so much for listening. This project was really fun to work on, and there's definitely ways to iterate and improve on it. For example, this implementation only uses Curve, and one might be able to get better execution prices if they use a DEX aggregate like 0x. If you're interested in the code, it will be linked to in the description below. There will be more of these videos, so stay on the lookout if you enjoyed it. Until then, happy to chat on Discord or Twitter. Thanks again and talk soon.